less than x plus m less than or equal to n plus m. Okay? Completely legal. Okay?
That's just by addition, right?
Yeah, that's simply by addition. Okay? It's an inequality rule. Okay? And it's an inequality rule of addition. Okay? So we're just going to say by addition. Okay. So, just looking back at the previous proof, okay, or maybe you just know, okay, what would the next line look like if we were to try to convert that back into the definition, or using our definition of ceiling? Anybody think they might know? So, Greg, go ahead.
Ceiling of n plus, or x plus m equals n plus m.
So, ceiling of x plus m
Would equal n plus
would equal n plus m. Okay? That's the very definition of what that we just said was, okay? So all we're doing is we're just basically thinking of it like we're just getting the definition, we're adding m, okay? And we're just transforming it, okay? For those of you guys that suffer through differential equations, Laplace transforms, you transform it into an algebraic, you solve it, and then you can solve it as a differential. Same sort of thing, we're just transforming it into, yeah, a lot easier said than done, right? Yeah, those are painful, by the way, so, sorry. All right, so this is our definition of ceiling again. And then guys, just like the last proof, what's the last thing we might do with this? Substitute back in for n, right guys? We know that n is the ceiling of x, okay? So we get the ceiling of x plus m is equal to the ceiling of x plus m, and that's just by substitution. I'll get every guy's way so you can copy this down. Alright, nice and easy, right guys? It's not meant to be difficult. Okay? Just like we said before, by above the original statement is true. Okay? So, by above this statement is true. Okay, so let me let you guys gander at that. And if you guys have some questions for me, I'd be happy to answer whatever I can. Okay? Go ahead, Greg.
So you're saying that ceiling of x plus m equals ceiling of x plus m,
Correct. For any integer n.
and it's
Right.
not it's equal to the ceiling of x plus m.
Correct.
Okay.
And if you want to, you can just start thinking of some numbers just to verify it for yourself. Okay? It does work, I promise. At least for the last 12 years that I've taught it, it's worked. Maybe it changed. I don't know. But I'm just messing with you. It hasn't. Okay. Other questions, guys, I can answer about this? Okay. All right. Let's do one more, but this time there's a condition that's imposed upon our last proof. Okay? So for the last one we have here, for all even integers, n, the ceiling of n squared divided by 4 is equal to n squared plus 3 over 4. Okay? So we can see that this is, what's that? Oh, I'm sorry, did I say even? Yeah, that's probably not a good idea then, because then it wouldn't be true, and then we could just say we're done with it. So, sorry, no, I would just impose about 10 more minutes of pain. All right. You might just want to pick like an odd integer, just to see if it works. Okay, let's just pick something basic. Let's pick 3, might as well. Okay, so again, just to verify that this works. So 3 squared over 4 ceiling is equal to 3 squared plus 3 divided by 4. Let's see if this works. Okay, this is 9 over 4. 9 over 4 is 2.25. Ceiling of that is 3, right guys? Over here, 3 plus 3, or I'm sorry, 9 plus 3 is 12. 12 over 4 is going to work out to be 3, right guys? So it looks like it works. Just for a trivial case, okay, we don't have to plug in something like 1001, although it would probably work for 1001 if we wanted to. So let's go ahead and prove this. Now with this one, we don't need the definition of floor and ceiling, right? Because don't we already have something that we can use a definition for? The odd number. Okay, so let's just use that and see if it works. Okay, so the only variable we need is just integer n, and we're going to define that to be z odd, right guys? Because we're told that for all integers, or for all odd integers, n. Okay, so let n be an element of the integers odd. Okay, arbitrary but particular. And you guys know the definition of odd. That's going to be equal to 2k plus 1. Might as well use it. Okay, so by definition of odd, n is equal to 2k plus 1. Okay? Most of you guys did a really nice job with this. A couple of you guys on the assignment that I just graded forgot to define the variable. Okay? If you forgot to define variables in this assignment, I just circled it and say don't do this again. I just defined it for you. But as we go along and we're getting more mature with our proof process, we want to make sure anytime we instantiate a new variable that we define the domain of that variable. Okay? All right. So does anyone think they might have a suggestion at this point once we've gone through and defined n to be odd?
Plugging in,
It's
substitution.
substitute, right? Let's just substitute into both sides of what we're given. Okay, sounds good to me. We usually do with even and odd. So by substitution, this becomes the ceiling of 2k plus 1 squared divided by 4. And we're hoping that that equals the quantity of 2k plus 1 squared plus 3 divided by 4. Okay, so that's just straight substitution. We are not using the definition of floor and ceiling for this one because we're already given a predicate condition that's saying it's already going to be odd. Okay, so we don't have to worry about that. Okay? What seems like the most obvious thing to do at this point?
Expand it.
Expand it out, multiply it out, right guys? I mean, every time we've had something squared, we've had to expand it. So let's do that, okay? If we were to FOIL this out, 4k squared, please don't say 4k squared plus 1, plus, not 2, but
4K.
4k, good. And then plus 1, right guys? Okay. And by the way, if you don't know how to do that, what do? You just write it off to the side and you FOIL it out, right guys? So what you guys can do is just do 2k plus 1, 2k plus 1. That becomes 4k squared plus 2k plus 2k plus 1. In other words, 4k squared plus 4k plus 1. Okay? So, I'm assuming most of you guys are good with that. Okay? But if not, just go through, do the algebra, knock it out that way. Okay? Won't hurt my feelings either way. As long as you get it right, you don't cheat. Alright. On the right-hand side, same exact thing, except we have a plus 3 in the numerator. Okay? So, 4k squared plus 4k plus 1 plus 3 give 4. So, that's just by FOIL, multiply, expansion, polynomial rules. We'll just say multiply. Okay. So, I'm guessing everybody knows what to do on the right-hand side of this, okay? 1 plus 3, okay? That's easy. What about the left-hand side? Does anybody think they might know a way that we might be able to prove this thing, Michelle?
You could just factor out the 4 from the first 2 terms, and then you could, then you'll have 1/4 in your credit.
Oh, okay, so maybe just break it up into maybe 3 fractions, or factor it out, whichever way you want to do it. I like your way too. I was going to do this, and I don't care which way you do it. I like your way fine, because you can cancel it out. I was going to do this, have it as 4k squared over 4, plus 4k over 4 plus 1/4, and I think we both arrive at doing the same thing. We get that 1/4, because I think you see that you need that 1/4 to make this work. Okay, nice. Okay, and that's legal, right, guys? We're dividing by a monomial. You can break it up into 3 separate components. Could we do the same thing on the right side? Sure. Okay, we could break that up into 4k squared over 4 plus 4k over 4. And then you guys know 1 plus 3 is 4, so we'll just say 4 over 4. Okay? That's just division, okay? Everybody sees that. That's something that we've done probably more times than we ever care to count in our lives. Okay, so just some division there. What's beating ourselves upside the head for us to do now? Yeah, simplify it down, so let's simplify it, I mean, that's why we broke it up, good. So inside of the ceiling, this becomes k squared plus k plus a fourth, right? On the right-hand side, k squared plus k plus 1. Okay, that's nice and easy. Okay, again, that's division if you want to call it again. So 2 division steps. And Michelle, was that what you were thinking, like to get down to? And whichever way, like you just factored out the first 2 and it still worked out nicely. Good stuff. Okay. So, does anybody have a suggestion at this point as to what's going to go on with this? So, Brian, what do you think?
Isn't doing that the same thing as taking the ceiling of each individual term?
Unfortunately not. Okay, so it's not a linear process. Okay, like for example, okay, let me just give you an example of that one that wouldn't work. Like if I had this ceiling of 1.9 plus 1.6 equals ceiling of 1.9 plus ceiling of 1.6. Okay, actually that wouldn't work. I lied. So there we go. But wouldn't this become 2.7? Ceiling would be 3. Ceiling of this is 2, ceiling of this is true. So is 2, and 3 obviously doesn't equal 4. So unfortunately, it's not a linear process, okay, meaning you can't distribute that. So good try, okay, but unfortunately not. Any other suggestions, guys? So, Michelle, go ahead.
K is integer, so that isn't explicable.
Okay, so you have an integer plus an integer plus a fourth, right? So let's say k was like 1. 1 plus 1 plus a fourth just goes up to what, guys? 3. It just goes up to the next integer, right? You're on the right track, okay? I think what you were thinking was right for this problem because they're integer values, okay? So, guys, the ceiling of k squared, because it's an integer, isn't it still k squared?
Mm-hmm.
The ceiling of this k is an integer, so the ceiling is going to be k. But the ceiling of 1/4 is going to become what, guys? 1.
Yeah.
So doesn't this just, oh my god, I almost forgot it with this. How many of you guys have seen one of the teachers write on your pad? And they're like, oh my
Yeah, I
god.
was looking forward to seeing it for the first time though.
Wow. So you're going to let me do that? Wow. Man, that's like cool, bro. I thought we were cool.
I would let them know too.
Shut up, Dom. Alright. But guys, that becomes k squared plus k plus 1. That's the very definition of what the floor function does, right? Integer plus any decimal just goes up to the next integer. The right-hand side is static. There's no more operands to perform there. K squared plus k plus 1. We done, right, guys? That's the definition of ceiling, by the way. And remember, k has to be an integer, right? But didn't we define k to be an integer at
Yep.
some point? We did right there. Okay, so we're straight. Okay, we didn't do anything illegal, not yet. Okay, so this is our definition of floor. Oh, ceiling. Oh. Yeah, that'd be bad to use the definition of floor when it's clearly a ceiling proof. Okay.
Or you were thinking about drinking.
Yeah, that's true. That's a good excuse. I like you again, James. Okay. So,
Can I ask you one question?
sure, go ahead.
If it was a floor, then it would have become 0, right? K squared
That's
plus
correct, okay, that's actually important, because there might be one on the homework like that, okay? Let's say, and let me write that on the board, let's say you had this, the floor of k squared plus k plus a quarter, okay? Or what were you saying that becomes?
0.
Okay, well, not the whole thing, but k
K
squared,
squared plus k plus 0.
right, okay, because it's a floor, and the floor of the quarter is going to be 0. Now that's only if k is an integer, right guys?
Uh-huh.
So, if k is not an integer, if k is real or rational, all bets are off. You can't say anything about that, okay? I think on your homework, that's going to be helpful, okay? So make sure you guys use that. I don't know which question it is, but when we're done, if you guys remind me to look at the homework, I can give you guys some hints. You have it, Donnie? Do you mind looking it up real quick and seeing? There should be one that says either even or odd or something like that. Number 4, is it? Or,
Number 8.
oh, it's number 8. Take a look.
Yeah, I see it, yeah.
What does it say?
For all x, if, the e thingy is zi,
Okay.
n squared over 2, floor equals n squared minus 1 over 2.
Okay. And so what you guys are going to do is you're going to use it's not gonna look like this, okay, but you're gonna use this principle to be able to verify that, okay? So basically, guys, just make sure you remember that this does work for this sort of thing. You'll eventually get, I think it'll end up being like 4k squared plus 4k plus 1 over 2, like that. And then when you break it up, you get the floor of a half. Okay, so, and if you guys, of course, if you guys need help, you just come to my office. I'll be happy to help out. Okay. All right. So, by the way, that was really important. So, did you say that on purpose because you started working on
No, I
it?
was thinking about it.
Okay, that's a good thing to think about. So, good stuff. Yeah. So, make sure you guys use this for number 8. It'll be a lot more helpful than just trying to bully it and do something that you're not supposed to. Okay. Other questions, guys? Okay. So, I think we just have to write that last line on here and we're done. So, 5 statement is true. Okay. Alright, so we're done with direct proof, at least for now. Okay? Now we're going to start looking at a secondary methodology of proof, which is even more powerful, something called indirect proof. Okay? And there's actually 2 main methods that we're going to use for indirect proof. Okay? So, one of them's really easy, and then one of them's more difficult. Okay? The more difficult type is called method of contradiction. Okay? So, guys, remember, contradiction, okay, or what we're going to say with contradiction is, we're going to write the negation. Okay? Sometimes we can't prove something is true, but we can prove that its negation is false. Okay? Because remember, guys, a statement is either true or false, right? It's one of the two. Okay? Like, for instance, if I said, Donnie, how much money is in my wallet right now? Huh?
None.
None? Okay. So I come out, oh man, I'm balling today. I got $20. Yeah, man, I'm gonna just put this right in my nose later. But no, you're wrong, and so you were incorrect. Right? It's either you're wrong or right. Okay. So